I want to show you something that should genuinely bother you. Watch this. GPT-4 scores in the 90th percentile on the bar exam. It can write code, explain quantum mechanics, compose poetry indistinguishable from human writing. It has processed more text than you could read in 10,000 lifetimes. By any reasonable measure, it's one of the most capable systems ever built. Now watch what happens when we ask it something simple. Catch a ball? A 3-year-old can do this, a dog can do this, any creature with eyes and limbs figured this out millions of years ago, but GPT-4, completely helpless. Now here's the thing, this isn't just a fun quirk. This failure points to something deep, a fundamental gap in how current AI systems understand the world. And here's why you should care. If you understand why this fails, you understand one of the most important frontiers in AI research right now. So let me ask you directly, why do you think this happens? Take a moment. What's your hypothesis? Is it that language models aren't big enough, not enough training data, wrong architecture, or they're pretending to be stupid so we let our guards down and they take over the world? Think about it, then I'll tell you the answer. Here's the answer, and it's surprisingly simple once you see it. Language models, as the name implies, learn from language, aka text. Not from the world, but from text about the world. ChatGPT has read billions of pages describing balls falling, cups tipping, gravity, pulling. It knows that he dropped the ball is usually followed by it hit the ground. It has learned to predict that that is the most likely thing that follows he dropped the ball from what it has read, not seen, but only read. And this is the key insight. Knowing the words for physics is not the same as understanding physics. Let me make this concrete. Have you ever read a book about riding a bicycle? Did reading it teach you to balance? Of course not. You had to actually get on the bike and fall. Reading about balance doesn't teach you balance. Reading about gravity doesn't teach you gravity. Text is a description of reality. It is not reality itself. An LLM is like someone who memorized every physics textbook ever written but has never actually seen an object fall. So here's the question that drives this entire video. How do we build AI that actually observes the physical world and hence can predict the next thing in the world? This is what world models are. And by the end of this video, you'll understand exactly how they work, the mathematics, the architecture, and the clever tricks required. Let's begin. Before we can understand world models, we need to be clear about what they're replacing. So let's spend a few minutes on how language models actually work. Even if you know this, seeing it precisely will make everything else click. Here's what we'll cover: tokenization, next token, prediction, and then critically, what's missing. That gap is where world models come in. When you type a sentence into ChatGPT, the model doesn't see words. It sees tokens, chunks of text, typically 3-4 characters each. This tokenization process takes an input of words and outputs tokens. Here's a real example. The sentence, "The robot picks up the ball," becomes exactly 7 tokens. The token 464, robot, token 13027, picks, token 23097, up, token 510, the token 262, ball, token 42206. Notice the spaces are included in some tokens. This matters for how the model processes text. Now, here's the crucial constraint. GPT-4 has a vocabulary of exactly 100,000 tokens. A vocabulary is just the set of unique tokens. Every single output must be one of these 100,000 options. Nothing else is possible. Why does this matter? Because it means text is fundamentally discrete. It's one token, then another, like beads on a string. Keep this in mind. We'll need it in a moment. Now, here's the core mechanism. This is genuinely elegant once you see it. Given all previous tokens, the model outputs a probability distribution over all 100,000 possible next tokens. Let me trace through this concretely. Input. The cat sat on the model computes 100,000 probabilities, one for every possible next token, and these must sum to exactly 1. It's a proper probability distribution? Maybe. Mat gets 0.67, most likely. Floor gets 0.12, rug gets 0.08, table gets 0.04, and tiny probabilities for the remaining 99,996 tokens. To generate text, we sample from this distribution. Maybe we pick mat. Now the input becomes the cat sat on the mat, and we repeat the whole process. That's it. That's the entire algorithm. Predict a probability distribution over next tokens. Sample 1. Append it. Repeat. Now that cat example was very simple, but imagine this when the vocabulary is the entire internet. That explains how systems like ChatGPT can talk about Shakespeare, string theory, history, and programming languages. Every conversation with ChatGPT, every code completion, every essay, it's all this mechanism running millions of times. Let's write this mathematically. This equation is important. We'll compare it to the world model equation in a moment. P of x or t given x01, x02 through x or t1. Breaking this down, P means probability, x or t is the token at position t. What we're predicting, the vertical bar means given or conditioned on. x1 through xt1 are all previous tokens. In plain English, the probability of the next token given all tokens before it. Simple, elegant, trainable on any text corpus. But now look very carefully at what is not in this equation. There's no state, no representation of where objects are in space. There's no action, no way to ask what happens if I do this. There's no physics, just statistical patterns in text. This equation models language. It doesn't model the world. If you ask what happens when I drop this ball, predicts what words typically follow that phrase. It doesn't simulate gravity. It can't. There's nowhere in this equation for gravity to live. So here's the question. What would an equation look like that actually models the world? That's what we're building toward. Here it is, the world model equation. Look at both side by side. LLM P of xt given x less than t, next token given previous tokens. World model P of s t1 given st, at, next state given current state, and action. See that extra term? At, action. That's not just a small addition. That single term changes everything. An LLM asks, given the text so far, what token comes next? A world model asks, given the world right now, if I take this action, what state comes next? That if I take this action is what separates passive prediction from planning. Let me show you why this matters with a concrete example. Here's a robot arm near a cup. That's our state ST. Now I ask, what's the next state? And you should immediately think, I can't answer that. What's the action? Exactly. Without knowing the action, the future is undefined. Watch. If action equals move left, arm shifts, cup stays put. If action equals push cup falls, possibly breaks. Same starting state. Different actions. Completely different futures. This is why robots need world models. Before moving, a robot can simulate, if I do action A, what happens? What about action B? What about C? It can explore thousands of possible futures in imagination, find the best action sequence, then execute it. Fail in imagination, not in reality. When you're controlling a surgical robot or a self-driving car, this matters a lot. But here's the problem, and this is where it gets interesting. What is the state of a video frame? A single 1080p frame, 1920 x 1080, which is the total number of pixels times 3 color channels per pixel. 6.2 million values. That's 6.2 million numbers we need to predict every frame. Now here's a question for you. What's the problem with predicting 6.2 million values? And I don't mean it's a lot. There's a deeper problem. Think about it. If you get pixel 1 slightly wrong and pixel 2 slightly wrong and pixel 3, what happens? The errors don't just sit there, they compound. Because your next prediction uses your previous prediction as input. We need a fundamentally different approach. This is where latent space enters. And for the first time, you'll understand why latent space actually exists. The solution is compression, but not like a zip file. This is learned intelligent compression. An encoder neural network, that's job, is to encode stuff, takes those 6.2 million pixel values and compresses them to a latent vector, typically around 1024 values. That's the encoding. Let me put real numbers on this. 6,220 800 pixels goes to 1,024 latent values. That's a 6,000 to 1 compression ratio. Quite a jump in efficiency. But here's what makes this special. This isn't throwing away 99.98% of the information randomly. The encoder learns what to keep. What does it keep? Object positions, shapes, velocities, spatial relationships, things that matter for physics. What does it discard? Exact pixel colors, texture details, lighting nuances, noise. A red ball and a blue ball in the same position might have wildly different pixel values, but their latent representations will be nearly identical, because for physics, color doesn't matter. Position does. We predict in this compressed space, not 6 million pixels, 1024 meaningful values. Let me show you quantitatively why compression helps. Imagine each prediction step has 1% error. That seems tiny. After one step, 1.01 equals 1% error. After 10 steps, 1.01 to the power of 10 equals 1.105 equals 10.5% error. After 50 steps, 1.01 to the power of 50 equals 1.645 equals 64.5% error. After 100 steps, 1.01 to the power of 100 equals 2.70 equals 170% error. This is exponential growth. The errors don't add, they multiply. Each prediction feeds into the next. In pixel space, you're making 6 million predictions. Any error, a slightly wrong shadow, a misplaced texture, compounds. In latent space, you're making 1,024 predictions. And they're predictions about meaningful structure, not arbitrary pixel values. Does this eliminate error compounding? No, but it gives us a fighting chance. We're predicting the things that matter, not every irrelevant detail. So here's the architecture so far. 3 components. Encoder E takes an observation, video frame, outputs a latent vector, Z equals E of observation, dynamics model D takes current latent vector plus action, predicts next latent vector, Z T plus 1 equals D of Z at T, action T. Decoder G takes a latent vector, reconstructs the observation, observation equals G of Z, compress, predict in latent space, reconstruct, elegant, right? Now I want you to think about something. Where's the weak point in this system? Which component is going to cause problems? Think about what each component does. The encoder compresses, that's fine, we just lose some detail. The dynamics model predicts, that's the core function. The decoder reconstructs, the decoder, that's where the problem is. Can you see why? Here's the issue. The encoder throws away details. That's the whole point of compression. But the decoder has to recreate a full image. So it has to invent the details that were thrown away. What exact shade is that shadow? What texture is that surface? The encoder didn't save this information. So the decoder guesses. And here's the trap. The decoder's guesses might not match reality. Now think about what happens on the next time step. We take the decoder's output, including all its invented details, and feed it back as input. The model starts predicting physics based on artifacts it hallucinated. Frame after frame, the hallucinated details compound. The model drifts further from reality, not because it's bad at physics, but because it's predicting based on its own inventions. What if we could skip reconstruction entirely? This brings us to JEPA, Joint Embedding Predictive Architecture, and this is, I think, genuinely beautiful. Watch carefully. This is the key insight. Old approach: 1. Encode current frame to latent ZT. 2. Predict next latent ZT plus 1. 3. Decode to pixels. 4. Feed those pixels back as input for the next prediction. JEPA approach: 1. Encode current frame to latent ZT. 2. Encode future frame, the ground truth, to latent Z future. 3. Train a predictor to go from ZT directly to Z future. Never decode, ever. The loss function becomes L equals the squared norm of E of future frame minus P of E of current frame. Let me unpack this. E of future frame equals encode what actually happened. P of E of current frame equals predict what we think will happen. Take the squared distance between them. We're not predicting pixels. We're not reconstructing images. We're predicting representations. And this is a much, much easier target. Why is predicting representations easier than predicting pixels? Here's the intuition. 2 video frames show the same ball in the same position. Frame 1 is filmed at noon, bright sunlight. Frame 2 is filmed at sunset, warm orange light. Their pixel values, dramatically different. Millions of pixels differ. Their latent representations, almost identical. Because the thing that matters, the ball's position, is the same. Pixel prediction demands get 6 million values exactly right. The shadow must be this exact shade. Latent prediction demands get the meaning right. Where are objects? How are they moving? JEPA predicts what matters and ignores what doesn't. But, and you knew this was coming, this creates a new problem. And this one is sneaky. It's a failure mode that will completely derail training if we don't catch it. See if you can figure it out. What happens if the encoder learns to cheat? Here's the trap. The encoder can output anything. What if it learns to output the same thing for every input? Dog video goes to 0, cat video goes to 0, car video goes to 0, anything goes to 0. Now the predictor's job is trivial. Input is always zeros. Output should be zeros. Done. What's the JEPA loss? Distance between 0, 0, 0 and 0, 0, 0, 0. Perfect score. But the model learned nothing. It collapsed all information into a single point. It can't tell a dog from a car from a building. This is called representation collapse. And it will absolutely happen if you naively minimize the JIPA loss. The model found a shortcut. Destroy all information, predict nothing, achieve perfect loss. So the question becomes, how do we force the encoder to actually learn meaningful, diverse representations? The solution is VIC-reg, variance, invariance, covariance, regularization, 3 terms added to the loss. Each one prevents a specific failure mode. Variance term. Problem. What if one dimension of the latent is always the same value for every input? Then it carries 0 information. Solution. Require that across your training batch, each dimension has sufficient variance. Different inputs must spread out in latent space. Mathematically, for each dimension, j require standard deviation of zgj greater than threshold. Covariance term, problem. What if dimension 1 and dimension 2 always move together, both high or both low at the same time? Then they're redundant. You have 2 dimensions storing one piece of information. Solution. Minimize the off-diagonal terms of the covariance matrix. Force dimensions to be uncorrelated, each capturing something independent. Invariance term. This is the actual prediction objective. Predicted representation should match target representation. This is your JIPA loss. The full loss L equals lambda times invariance plus mu times variance plus nu times covariance. Variance prevents collapse to a single point. Covariance prevents redundant dimensions. Invariance drives actual learning. This is why modern world models work. It's not just clever architecture, it's careful regularization that closes every shortcut the model might find. Let me check if this is making sense. If I told you a world model was achieving 0 loss but producing useless outputs, you should immediately think representation collapse, add variance regularization. If I told you a latent space had 10 or 24 dimensions but only seemed to capture 10 distinct things, you should think redundant dimensions, add covariance regularization. If these feel natural, you understand VIC-reg. If not, rewind 60 seconds. This is important. Now, how do you actually train this? Here's something elegant. Traditional ML needs labeled data. Someone manually annotating this image contains a cat. World models use self-supervised learning. Think about it. Given frames 1, 2, 3 of a video, what's the training target? Frame 4? The next frame is the label. No human annotation needed. This is the same insight that made LLMs work. GPT doesn't need humans to label the next word should be X. The next word in the training text is the label. Self-supervision unlocks scale. You can train on every video ever recorded. No labeling. Just predict what happens next, compare to what actually happened, update. This is why world models are suddenly working. The ideas are years old, but only now do we have enough compute and data to train them properly. Real numbers. VJEPA2 from Meta 2024, 1.2 billion parameters, 1 million plus hours of video training data, that's 114 years of footage, 2,000 H100 GPUs for 4 weeks, cost millions of dollars. For context, GPT-4 is roughly 1,000 times larger and cost around $63 million. World models are on the same scaling trajectory as LLMs, just a few years behind. More data plus more compute equals better predictions. We're still in the early scaling phase. Let's connect everything back to the real world. Everything we discussed enables one core capability, predicting how the world changes in response to actions. Once you can do that, you can plan. You can simulate futures without living them. You can ask what if and get a real answer for applications. Video generation. Sora, Veo, type a prompt, get physically coherent video. The world model predicts frame after frame, maintaining consistent physics. Robotics. Before moving, simulate thousands of action sequences, find the best one, execute, fail in imagination, not reality. Game AI. Google's Genie generates playable worlds from single images. Player input drives the world model in real time. Autonomous vehicles. Predict what other agents will do. That car might turn, that pedestrian might cross. Plan for all possibilities. Every application is the same core, predicting how the world changes in response to actions. Let's trace the complete chain. Every concept earned its place by solving the previous problem. Problem: LLMs can't understand physics. Why? They learn from text, not observation. Solution: learn from video, world models. Problem: video is 6 million values per frame. Solution: compress to latent space. Problem: errors compound. Reconstruction introduces artifacts. Solution: JIPA don't reconstruct. Predict representations directly. Problem: encoder might collapse. Solution: VC reg force diversity. Throughout condition on actions, that's what enables planning. This is actually how the field developed, each innovation addressing the limitation of what came before. Quick recall. For each equation, see if you know what it means before I say it. P of XOR T given X less than T. LLM, predict next token. P of S type T was 1 given SRTAT. World model, predict next state given action. L equals the squared norm of E of future minus P of E of current. JIPA, predict in representation space. L equals lambda times in V plus mu times var plus nu times cov. Vic reg, prevent collapse. If you got those, you genuinely understand this field. Finally, honesty. Current world models score around 60% on physics benchmarks. Humans score 90%. The gap is real. They learn correlations. Balls usually fall, not causation. Long horizon prediction remains unsolved. This is cutting-edge research, not solved technology. But 5 years ago, coherent video generation didn't exist. Progress is real. Where does it lead? LLMs understand language. World models understand physics. The future is integration. Systems that can read about the world and experience it and understand both. We're not there yet, but now you understand the path. Thanks for watching.